charge. And I'm going to start by drawing us a quick voltage diagram for what's going on. I actually might draw a few of them. I take it back. I'll probably only. So here's my voltage diagram. I'm going to start by going over the battery. So there's a voltage gain that I have from the battery, and I'll just label that VB. And then I get over here, and I'm going to do after the switch has been closed for a few seconds, but not for a very long. So I drop some voltage over the resistor. I know that's how that's going to work. So I'll draw a little arrow for that. And then I also am going to have to drop some voltage over the capacitor. And I don't know exactly how big either of those voltage drop is going to be. So I've just drawn them as kind of arbitrary lengths, and I'll label them V over the resistor and V over the capacitor. Okay, that's what our voltage diagram looks like. The next question that I want to answer here is, what do Kirchhoff's laws have to say about the circuit? If I were to throw the junction and the loop rules at this circuit, what is it going to do? And I can be guided by my voltage diagram here, right? I already know that I'm going to need to add up these three voltages to get 0 because I'm going around a complete loop. And I also know from what we've done over the last couple of weeks, an expression for the voltage of the resistor and an expression for the voltage of the capacitor. And when you do that, this is what you end up getting, right? V battery is what it is. That's a constant. The voltage over the resistor is I times R, and it's negative because I'm dropping voltage. And the voltage over the capacitor is Q over C, and it's also negative because, again, I'm dropping voltage as I go from the top of the circuit to the bottom. I'm going to get back to our starter, and that's equal to 0. Then I'm going to use a really cool fact, which is that the current through the resistor is related to the charge that builds up on the capacitor by a derivative. I'm going to plug that in right there. And then I'm going to do some quick solving. And when I solve, the thing I'm going to solve for is dq dt. And you might know why I solved for that, because this equation, dq dt equals stuff that has q in it, is a differential equation. In particular, I might not get them all right here. It's a first order, linear, ordinary differential equation with constant coefficients, something like that. I probably missed one. But that's a thing that we know how to solve. We can look up the solution to that. Some old mathematician figured out the answer to this differential equation like 200 years ago. And I trust them. So I'm just going to go ahead and write down what the answer to this differential equation is, with the initial condition that the charge on the capacitor is 0. So that means the capacitor started out uncharged. And when I do that, the result that I get is that the charge as a function of time looks like this exponential function. And the current as a function of time also looks like an exponential function. And I've written both of those in terms of all the other constants that I know, the resistance of the resistor, the capacitance of the capacitor, and the voltage of the battery.